Swayam Prabha. Digital India. Educated India.
Hello and welcome everyone to this lecture series on the modeling of multiphysics system. So from the last lecture onwards, we have moved on to the segment for the multiphysics problems and modeling of these systems. In this segment, we have started with thermomechanical or thermoelastic materials and devices. So just a brief revision of what we have done in the last lecture to bring you up to the mark. So in the last lecture, we have seen what a thermomechanical device is. So thermomechanical device is something that converts thermal energy into an elastic or a work output. So we have devices or systems which convert thermal input, and thermal input can be in the form of resistive heating, I square R. It can be some inductive heating or some other source of heat and generation. That heat generation can either be indirectly converted to an elastic energy, that is deformation or motion in some form, can be directly converted into deformation. Okay. So devices which convert thermal input into a mechanical output are called thermoelastic devices. So in the last class, we have gone over 6 different examples of thermoelastic device, which included something which we called as pneumatic devices, in which there was the link between the thermal energy to the mechanical deformation was through a gas which expanded under heat. That expansion of the gas, it caused pressure onto a membrane or onto a film or to a plate, and that plate would deform. Then we have systems that are linear thermoelastics, V-beam actuators, shape-shift alloys, etc. Right. So all of these materials or devices, they take in thermal input in some form, and they give out a mechanical response or an elastic response. Okay. So in the last class, we started with the modeling of a thermopneumatic device. So I'll just write down the equation so that we can continue from that point onwards. So a thermopneumatic device, we had a cylinder with a piston connected to a spring. Now the bottom of this is heated by an electrical heater. So we have an electric heater at the bottom. The heating of this gas that is filled inside would cause the gas to expand according to the ideal gas equation, PV is equals to nRT. So as temperature would increase, the volume would increase to maintain a constant pressure, and that would cause this membrane to move up. So we will have a displacement along x direction. Okay. What we had seen from this is we had 2 sets of equation. The first equation was from Newton's second law. So from the Newton's laws of motion, we derived that the mass times the acceleration, that is md square t by dx square equals to minus kx plus nRT over L plus x. Okay, so this was our spring force, and this was our pressure force due to the expansion of the gas. All right. So we had this gas that was expanding and the spring that is trying to pull down the plate. The 2 forces will balance out each other, and whatever acceleration or force, the residual force is being left, that force would cause the body to accelerate, and that is mass times acceleration due to the unbalanced forces. Eventually a point will come when the forces will balance out and the system will go into steady state. This was the first form of equation. The second set of equation was formed on the conservation of energy. So, from the conservation of energy, we found out that the net heat being stored in the gas is equal to the heat being input and the heat being dissipated. So, the heat being input is through convection, that is minus HAT minus TH. TH is the temperature of this hot plate, and T is the temperature of the gas, and then the heat is being given out in the form of the pressure change and the expansion of the piston. So, from the conservation of energy, we derived our second equation, that was KNR dt by dx plus HA T minus TH will be equals to minus NR over L plus X dx by dt. Okay. So, this came from the first law of thermodynamics, that is, the net work done was equals to the net heat added minus the internal energy change, or the other way around. So, we can say that du is equals to dq plus dw. So, the net work done is the internal energy change minus the heat input from the given system. Okay. So, this becomes our internal energy change, this is the heat input, and this is the work done. All right. So, with these two equations, we can see that our equation for x depends upon t, that is the first equation. Our equation for t dependent upon x. What we did is we tried to come up with an expression that was non-dimensionalized with two constants, that was alpha and beta. So, alpha was equals to, when we normalize this, was equals to Nr into T hot, the hot plate, over KL square, and beta was equals to square root m by k into HA over capital K Nr, the small k. All right. The difference of the two is that alpha is the ratio of the pressure force to the spring force, and beta is the ratio of the oscillation time scale to the thermal transport time scale. So, based upon this, our system could be modeled. We have seen how to solve this analytically, and analytically we cannot solve this coupled equation. It becomes very difficult to implement the mathematical techniques to solve this. On the other hand, if you would convert this into a steady state problem in which d square x by dt square becomes 0, and d square x by dt square becomes 0, and this dt by dx becomes 0. In that case, we can solve this, and that is what we have shown in last class. Now, in this lecture, we will start with the numerical implementation, that is where we left on the last class. So, the numerical implementation, if we write down our governing equation in the non-dimensionalized form, so, our first equation was non-dimensionalized as d square u hat by dt hat square plus u hat was equals to alpha 1 plus theta hat by 1 plus u hat. And our second equation was likewise written as d theta hat by dt hat plus beta into theta hat was equals to minus 1 by capital K 1 plus theta hat by 1 plus u hat du hat by dt hat. Okay. How did we non-dimensionalize? That theta hat was equals to t minus t hot by t hot. The time scaling was square root m by k into t, and our u scaling was x over L. Okay, so, this was our equations. Again, alpha and beta are a set of constants where all the material properties are linked together. What we are trying to solve is that this is the first order differential with time, which means that we need two initial conditions to solve the first one and one initial condition to solve the second one. That is fairly straightforward. If you have a second order differential, which means that we need a velocity condition and we need a displacement condition for u, and for the temperature case we need the initial temperature for the given system. All right. So, if that is known, then we can start by setting up a solver to solve this or implement this numerically. Numerically, we can solve this completely transient, we do not have to make any assumptions of steady state. So, developing a transient solver. Now, we need to see that this equation u depends upon theta and theta depends upon u. So, we need to make some approximations or some numerical approach, so that we can converge. And the first equation can be discretized. So, if we have a domain of cases time domain, so t hat going from 0 to say 1, we can discretize this into smaller segments. And if you go back to our initial set of lectures, I believe lecture 4 and 5 were dedicated on the development of this numerical methods. So, I would suggest you strongly to go back to those lectures and refer to the numerical methods. One division of this is dt. So, you could divide this up. We can then discretize this first equation by finite difference. And you will have u hat of I plus 1 minus 2 u hat of I plus u hat of I minus 1. We can do this because we are moving in time. We can shift this forward by one step and do it completely forward difference I by delta t square is equals to plus u hat of I plus 2. So, our time step of solving is I plus 2. This is equals to alpha of 1 plus theta hat of the given time step I plus 2 by 1 plus u hat of I plus 2. This we are trying to solve. Now, there are some approximations which we can make to simplify this down. One thing, we can assume a general matrix of u and a general matrix of theta. So, we can define our u vector u hat of we can say our initial displacements are 1. Let us take it from point 1. So, if you look at our solution, it starts from 1 onwards. So, let's define our initial conditions. For equation 1, we will have u hat at time 0 is equals to 1 and du hat by dt hat at time 0 equals to 0. For the second one, we will have theta hat of time 0 equals to some value 3. Let us just take these values for now. All right. Now, what we want to do is u hat we can define say ones of nt comma 1, which means that there are nt number of points in the time domain. So, we can define a vector of nt comma 1. This is our initial guess. Likewise, theta hat we can define as ones of nt comma 1 into 3. So, we can define a guess value set of 3. So, u and theta are guess values right now. We can use these guess values to calculate new values and we can iterate on top of each other to eventually converge and get a solution. All right. So, what we want to do is we can then write iteration index over here. So, it is say k plus 1, k plus 1, k plus 1, k plus 1. This is the kth index, where k is the iteration index and I is the time index. Right. What we are trying to solve for is this. So, this is of importance. Rest everything can go to the right and we can simplify this equation down. Likewise, for the equation 2, we can again implement finite difference and theta hat of I plus 1 minus theta hat of I divided by delta t plus beta theta hat of I plus 1 equals to minus 1 by k 1 plus theta hat of I plus 1 over 1 plus u hat of I plus 1 into du hat by dt hat at I plus 1. All right. Now, this equation is slightly different from the above. We can see that again we can write the iteration number over here k plus 1, k plus 1, k plus 1 and k plus 1s, and these we can take as k, and this is updated, you can take as k plus 1 and k plus 1. So, what we are doing, we are trying to solve for this, the minus sign over here, and this based upon everything else. So, you can take everything else to the right hand side, keep the unknown term to the left. With this, we are trying from the first equation, we are trying to solve for u I plus 2 of k plus 1, From here we are trying to set it up for theta I plus 1 of k plus 1. Okay. Now, this looks a little bit complicated especially if you are coming from a background that does not involve significant understanding of numerical methods. Try to write down a pseudocode to some extent. This is mostly written in a MATLAB format. You can convert into any other programming language format. Okay. So, the pseudocode for this is you define a time array. Okay. You find out dt, you find out nt, that is time stepping and the length of the time array. Now, you define a dummy u of k and theta of k. You can create a dummy vector of the length will be nt comma 1. So, it is a vector, it is a column vector of nt comma 1, you fill it up with dummy values. Then you can say that uk for the first value, we know the value is 1, uk for the second value is equals to uk for the first value. And why is this? If you go back one slide, then we can see that our boundary condition is this, which means that u2 minus u1 over delta t is equals to 0 or u2 is equals to u1. Okay, so, this is our initial condition. So, we know this. So, uk for 1 is 1 and u2 is equals to u1. Again theta k for 1 is equals to 3. This is well defined. Now, you can define an error counter, error of 1, and an iteration counter, iteration of 1. Okay, up to this point is your initialization of all your vectors, setting it up. All right. Now, what we want to do is we want to estimate the values. So, what we will do is we will iterate everything till error has reached an error tolerance and the iteration has reached an iteration max. Okay, so, either the error has exceeded an error tolerance, the error tolerance is 10 to the power of minus 6. Once it has gone below 10 to the power of minus 6, then this while loop will terminate. Else when the iterations have reached a certain maximum iteration, say 101 iterations, again then this while loop will terminate. This iteration counter is necessary for these kinds of simulations, because if you do not put it and if the error does not approach or does not converge to the error tolerance, in that case it will go into an infinite loop and will keep on going. All right. Now, once this is set up, the first thing we solve for is a time loop for this, for the finite difference scheme for first equation. So, we will go for, we will go I is equals to 3 to nt, and then we will write this equation. Again, I have taken I plus 2 as the current time step. We can convert this as I as current time step, and we can say, so these values are known, this is unknown. So, we can update our equation and we can find out u of I in terms of uk of I minus 1, uk of I minus 2. These are defined previously. Over here. So, uk of I minus 1, I minus 2 are defined previously, and as we will proceed these will be defined, plus, so a function of these, plus our uk values from the guess, uk and theta k values from the dummy matrix or dummy vector. You can end this. All right. So, this is our time loop for u. Now, we can define a du, which you can use, say, a gradient between t and u. So, you can find the gradient of u as a function of derivative with time. So, du is your gradient. Now, you can start your for loop for your time, say I goes from 2 to nt. In this for loop, you can then find out theta k of I based upon some function of theta k of I minus 1. Theta k of I minus 1, since I is starting from 2, I minus 1 is 1, theta k of 1 is known, that is known for the k plus 1th iteration. Now, we are going into the k plus 1th iteration, plus from the dummy vector some function of theta k of I and uk of I. Okay. So, that is what we have done. We have taken this as a dummy and likewise this as a dummy. Why we have taken this as a dummy is that these values will make the system non-linear. If you take it as a dummy and if you iterate on top of each other, eventually it will gradually come to a convergence. So, the convergence now needs to be satisfied. You can end it over here. And how to check for convergence? You can check for error between uk plus 1 and uk. One way to calculate error is the absolute maximum. So, max absolute of u for the k plus 1th iteration minus u for the kth iteration divided by u for the k plus 1th iteration. Either you multiply this with 100 or you can take it as is, does not matter. As long as this error has reached a certain tolerance and you need to do an iteration update, iteration is iteration plus 1 and end your while loop. If you do that, this is type of plot that you can expect where u is varying as a function of time. We have taken u of 0 as 1 and du by dt of 0 as 0 and we have taken theta of 0 as 3. Okay, that is our initial conditions. For the two equations, our temperature we can see is decaying and that is what we will expect. As the energy gets dissipated and the gas expands, our heat energy will get dissipated and temperature will go down. Our u is going to increase and we can see that the increase is non-linear. That is why these iterative processes are used in this case. I hope that gives you a sense of how to implement these kinds of code numerically. It is fairly straightforward once you get a hang of these methodologies. It is very easy to set the program up. Okay, then we will go into the similar system, but instead of a solid plate with a spring expanding it up, we are considering that we have the same cylinder as before, but instead of a plate we have a membrane on the top. The membrane is a two-dimensional system, so it is a 2D membrane, which means that the thickness is negligible compared to the length and the width. This membrane is fixed at the two ends, so it is fixed at the two ends. We again have a coil at the bottom. We have a gas inside. The gas is expanding due to the heat of the coil and the hot plate below, and this will cause the membrane to deflect as such. Okay, so the membrane would deflect as such. Now, membrane analysis are slightly different from a piston analysis because there is the membrane is undergoing deformation, so it is undergoing strain and that strain is giving the displacement. Unlike that of a spring, there is a spring force. In this case, it is a membrane's elastic property that is giving the resistance against the deformation. All right, so a membrane of radius a is attached to a cylinder of length L the membrane deflects in the x direction. We can say that x is this direction. And the deflection is a function of the radius and time. Okay. Now, our equations earlier were one dimensional and that is where we were solving a set of ODEs. Now, we will try to solve a set of partial differential equation in which the membrane is deflecting and is a function of both radius and time. So, u is now a function of r comma t. The volume of the deflected membrane is given by v, which is the function which is equals to pi a square L, that is the original volume, plus the deflected volume, that is 2 pi integration from 0 to a u, which is a function of r comma t into RTR. Okay, so this is the deflected volume, this is the cylinder volume. Okay. So, summation of the two. Now, for the membrane, and the conservation of linear momentum for the membrane, this we have done earlier. If you go back to our set of equations, I believe there are 6 set of lectures for solid mechanics. If you go back to them, you will find out how the membranes equations were derived. What we got was that rho del square u by del t square was equals to mu del square u plus p. Okay, so this was our mass times acceleration term. This was our deflection term. So, del sigma ij by del xj, the stress variation within the body, and this was our body force term. Right. If we again assume an ideal gas relation, that P is equals to nRT over volume V, we substitute volume over here, and then we substitute this back into our equation. Our governing equation becomes rho del square u by del t square equals to mu del square u plus nRT over pi a square L plus 2 pi integration 0 to a u r dr. This becomes our governing equation. What we need two initial conditions. So, u at time 0 at for all r and some value, and del u by del t for all r at time 0 is some value. Two initial conditions, we also need two boundary conditions. If it is a circular membrane, as we have written over here. So, this is a circular membrane. In that case, del u by del r at 0 comma t is 0, and u at a comma t is equals to is fixed. If it is fixed at 1, we can check quickly. It is fixed at 1, so we can say it is fixed at 1. Okay. These are our boundary conditions for this equation. All right. Now, we are going into the thermal analysis. So, from the first law of thermodynamics, we do the similar analysis as last time, and we find out that k n r dt by dx dt by dt equals to minus I will explain in a second how this came up. Okay. So, this became our set of equations. If I go back a few slides and I show you the set of equations that we wrote earlier. So, dt by dt, this set of equations from the conservation of energy, we have our internal energy term, which is the same as now. Our convection term remains the same. This was pressure into volume change as a function of time, P dV by dt, if you look again in our last set of notes. So, in this case, this you get as del u by del t of r dr, and k n r dt by dx and everything else is the same. Okay. So, this becomes our internal energy, this becomes our heat in or the heat input, and this becomes our work done or the rate of work done for our given system. Okay. So, these two equations, again this is a first order time derivative. So, we need one initial condition, that is t at time t is equals to 0 is some constant a. Okay. Now, if we normalize these two equations, I will do this quickly. We are normalizing the equations, again theta cap is equals to t minus th over th, u hat is equals to u over L, r hat equals to r over a, and t hat is equals to square root mu by rho to t over a. Okay. So, this becomes our normalizing equation. This normalized equation we can substitute back into our governing equation. So, these are normalized variables. So, when we substitute this back into our governing equation, what we will get is del square u by del t hat square equals to del cap squared u plus alpha times 1 plus theta hat divided by 1 plus 2 integration 0 to 1 u hat r hat dr hat. Okay. Earlier it was 1 plus u hat only, now it has this 1 plus 2 integration of u hat r hat dr hat. Okay. This term is your volume change or the effect of volume change. Then the second equation will become d theta hat by dt hat plus beta into theta hat is equals to minus 2 over capital K 1 plus theta hat by 1 plus 2 integration 0 to 1 u hat r hat dr hat, and then this time derivative of 0 to 1 del u hat by del t hat of r hat dr hat. Okay. Again these two equations we have two constants alpha as far as n r t h over pi into mu into L square. As we have said, it was a pressure force over or the effect of pressure or the pressure force divided by the spring force. In this case there is no spring, but there is this membrane that is deforming. Since the membrane is deforming, therefore the stretch or the pre-stretch in the membrane which is resisting against the gas expansion is there. So, it is pressure force by the membrane force, and we can try to rewrite this equation in terms of pressure. So, the pressure is P naught into A square divided by mu into L. Okay, here multiplied A square at the top and bottom, pi into A square into L is the volume. That volume, if you divide nRT over volume, that gives you the pressure. So, this becomes your final pressure, final equilibrium pressure corresponding to TH. A square is the square of the radius of the system, mu into L. Again, this is our pressure force by membrane stretch, and beta in this case equals to pi h into A cube capital K n r rho over mu. Okay. And just like last time, it is a ratio of the oscillating time scale to the thermal time scale. In this case, oscillations is due to the membrane oscillation divided by thermal time scale. Okay. Same set of equations that we have derived over here. Now, analytically it is again difficult. We can see that both the equations are coupled. This is equation 1, this is equation 2. U hat depends upon theta hat depends upon u hat. This set of equation is even more complicated than the spring mass case, because we have an integral term and we have a differential term within the integral, which makes this equation set difficult to solve for or difficult to implement. So, what to do is if you want to solve this analytically, so analytical solutions we need to make some assumptions. The first set of assumption is that we consider it under steady state. If it is under steady state, then our equation reduces to del u hat square plus alpha 1 plus theta hat over 1 plus 2 integration 0 to 1 u hat r hat dr hat, this is equals to 0. What we took away is this del square u by del t square term. Alright, now this equation is still a non-local equation, and what we can do is to simplify this by taking this as lambda. If we take this as lambda, then for a circular membrane this is d square u hat by dr hat square plus 1 by r hat du hat by dr hat plus lambda is equals to 0. The solution for this with the boundary conditions that u hat of 1 is equals to 0 and du hat by dr hat of at the initial of 1, that is correct, of 0 is equals to 0. These are our boundary conditions. We will get that u hat of r hat will be equals to lambda by 4 1 minus r hat square. Quick check is that u hat r hat of 1 is this becomes 0 and the derivative of this will be equals to 0 at r hat equals to 0. All right, very nice. So, now we have an expression, but we still do not know what this lambda is. So, the lambda term with u of r hat substituted from where? Substituted from here. We will get lambda is equals to alpha 1 plus theta hat divided by 1 plus 2 integration 0 to 1. We have this u hat term, we will replace by lambda by 4 r hat dr hat. Now, if we try to solve this equation for lambda, we will get an equation that is lambda square plus 8 lambda minus 8 alpha is equals to 0. All right. This equation, if you are again we are assuming the theta cap is very small, it tends to 0. For very small values of theta cap, we are getting this solution. This equation needs to be satisfied Okay, so the solution for this equation, if I write it over here, the solution for this equation will come out to be two values. Lambda will be equals to minus 4 plus minus 4 square root 1 plus alpha by 2. Now, one case is whether it is positive and it is negative. Now, say lambda 1 is minus 4 plus 4 root 1 plus alpha by 2 and lambda 2 is minus 4 root 1 plus alpha by 2. Now, alpha is always positive, 1 plus alpha square root is positive. If we take this negative term, then our lambda will become negative and our u will become negative. Now, if u is negative, that is fine, that is not a problem. Negative means that it is deflecting inwards. We can see that this value will become greater than minus 4 and u hat is lambda by 4. That means u hat will be greater than minus 1. That is not possible, because minus 1 is where it will hit the bottom plate. If it hits the bottom plate, it cannot go beyond the bottom plate, and that is not a practical solution. Therefore, this is not feasible. Therefore, lambda is equals to minus 4 plus 4 square root 1 plus alpha by 2. For a case where lambda tends to 0, this value lambda will be equals to alpha, which means that our u hat will be equals to at for 0 equals to n r th over 4 pi mu into L. Okay, so u hat of 0 is lambda by 4, lambda is equals to alpha. And if we go back over here, alpha is defined over as nrth over pi mu L square. So, it should be pi mu L square. Okay, that is your initial displacement or the maximum displacement deflection at steady state. Okay, so just let me quickly repeat this. Is we have taken steady state, we have considered this constant over here as lambda, and we solved this equation considering that lambda is a constant, and we got this expression for u hat as lambda by 4 1 minus r hat square. Now, if we take this expression for u hat and substitute back into the lambda equation, considering that theta is very small, in that case we get an equation for lambda as lambda square plus 8 lambda minus 8 alpha. When we solve this equation, we can get two solutions of lambda. One is not feasible because your u hat will become less than minus 1, and that is not a practical case. Other case is what we are considering. Now, if alpha is very small, in that case we can consider alpha tending to 0 and lambda will be tending to alpha. In that case, u hat of 0 will be equals to nrth over 4 pi mu L square. This is the maximum deflection of the membrane. It is positive, and it is the maximum deflection of the membrane at the center. Now, if you are looking for the numerical implementation of these equations, then let us first write down our governing equations. The first equation is del square u by del t square is equals to del square u hat by del r hat square. So, we are doing it in cylindrical coordinate, del u hat by del r hat plus, let me quickly write these equations down, plus alpha 1 plus theta hat divided by 1 plus 2 integration 0 to 1 u hat r hat dr hat. The second equation was del theta or d theta hat by dt hat plus beta into theta hat was equals to minus 2 over k 1 plus theta hat divided by 1 plus 2 integration 0 to 1 u hat r hat dr hat into integration 0 to 1 del u hat by del t hat into r hat dr hat. So, these two equations we are trying to solve. Okay, now the equation sets are more complex. We will have two initial and two boundary conditions for this first equation. For the second equation, we will have just one initial condition. With that in mind, we will try to again discretize this expression. So, u is now, say we start with 0, we start with ones, nr comma nt. So, you have created a grid for u. The u grid is a function of r comma t. So, this is a radial direction, this is a temporal direction. So, u is equals to ones of nr comma nt. We can define our initial condition that u for all r comma 0 is equals to 1. U del u by del t for all r comma 0 is equals to 0. That is initial it's flat and initially there is no velocity, and these are our initial conditions. Then our boundary conditions, we have u at 0 comma time t del u by del r equals to 0 and u at 1 comma t is equals to 0. That is, the edges are fixed and the center one it is asymptote, it becomes flat, right. So, that means the left hand side and right hand side are symmetric and the model is axis symmetric. Okay. Likewise, you can define your theta as some ones of nt comma 1 and your theta has an initial condition of theta of 1 is equals to some value, say 3. So, you have defined some initial condition. Now, just like last time, we can discretize this equation again. So, the first equation we can discretize by finite difference. We can say that u for n plus 1 or nth time step I minus 2 u and I minus 1, this makes it very similar to a MATLAB code, by delta t square is equals to u of n minus 1 I plus 1 minus 2 u of n minus 1 I plus u of n minus 1 I minus 1 by delta r square plus 1 over r of I u of n minus 1 I plus 1 minus u of n minus 1 I minus 1 by 2 delta r. This becomes your this u term, that is your Laplacian term for u, and plus alpha 1 plus theta of I for the given time step divided by 1 plus 2 integration 0 to 1 u of I for the given time step r of I dr. Okay. Now, again we can see that this part is where it is getting non-linear. To make it linearized, we can take these are initially dummy values. So, you can take the dummy values over here. So, our dummy vector, and likewise solve for u n of I using all the other terms. So, n minus 1 and I minus 1 or I minus 1 I minus 2 are all known. All right. I am sorry, I wrote this wrong. Let me correct it quickly. N minus 1 and minus 2, where n is the time index and I is the space index. We are doing this with an Euler explicit scheme. Our second equation we can likewise discretize as theta. Now, theta is only a function of time, not a function of space. So, theta of n minus theta of n minus 1 by delta t plus beta theta of n is equals to minus 2 over k 1 plus theta of n divided by 1 plus 2 integration 0 to 1 u of n I r I dr integration 0 to 1 this del u by del t term for the ith location and nth time into dr. Okay. And r dr, I am sorry, r I dr. So, we are trying to find out is this theta n, these two are the unknown terms. This theta n you can take for the kth iteration, these you can take for the k plus 1th iteration. Likewise, for the last one, this you can take for the k plus 1th iteration, and all of again k plus 1, these are the other values, and this set, the last set you can take for the kth iteration, the nonlinear term. So, alright, so this part is your nonlinear term, and you can take for the kth iteration and solve. Un, because you have already found, you can find it for the k plus 1th iteration. So, whatever is known, so you can first solve for u taking the dummy values of theta, and then you can solve for theta taking the calculated values of u. Okay, that if that makes sense. So, this becomes a semi-implicit form of application, and we can iterate this. So, the approach will be the same, you define an error value, you define an iteration value, and then you define a for loop, a while loop for error greater than error tolerance, iteration less than iteration maximum. All right. Now, we have time loops for the Euler explicit for the first equation going from 3 to because we have n minus 1 and n minus 2. So, we have it going from 3 to 20. What we are trying to get is u of n I, and we will have a set of terms for u of n minus 1, u of n minus 2, values of I minus 1, I plus 1, and so on. So, these are for the kth iteration, k plus 1th iteration, what is getting updated, and then you will have this nonlinear term, which will be u for n of I and u theta of n of I for the kth iteration, the last iteration of the dummy values. So, this is known current iteration, and this is the unknown, so dummy value from last iteration. Okay. We will do this in space. So, if you are doing this in space, we will need a space loop. So, we will have for since it is space is going from a second order derivative over here del square u by del r square. So, we will go I from 2 to n r minus 1. So, in space we have gone from 1 to n r and from 1 to n t. So, so you will go space loop 2 to n r minus 1. And we will solve for all of these u of n I in terms of u of n minus 1 I plus 1 I minus 1 and u of n minus 1 and n minus 2. Okay, solve for all of these, end the space loop, put in your boundary conditions, that is u n of 1 is equals to u n of 1 is equals to u n of 2, the k plus 1th iteration, and u n of last value, that is n r, is equals to 0, that is fixed. And we have taken it as 1, the displacement is 1. Okay, so these are your boundary conditions. Right, so this becomes our equation 1, or a set of codes for equation 1. Now, for equation 2, what we need first is we need to define this du, and then you can use your gradient between t and u. Again, u is a function of r and t, just make sure that you have taken a derivative along time and not along space. These integrals, I may have forgotten to mention even in the last set when we were doing the mass and spring, these integrals you can solve using trapezoidal rule. So, you can use trapz in MATLAB and you can do this integration of u comma r. Alright, likewise over here you can solve these using trapezoidal rule, you can use trapz. Likewise for this trapz. All right. Now, for the last set, you will again do a time loop. In this case, the time loop will go from 2 to n t, and you will calculate theta n based upon theta of n minus 1 and this non-linear term, which will depend upon theta of n and u of n. This will be for the kth iteration and k plus 1th iteration. So, use the last set of values for u and use the dummy values for this nonlinear term for theta n. What is this nonlinear term? This theta n of k. You end this. This is already initialized. Now, you can find your error just like last time. Save these values into a dummy vector from the last iteration. You can update that value. If someone who does not know how to do that, then u of L is equals to u, and you can say theta of L is equals to theta, and then error you can find out as maximum absolute of say u for k plus 1 minus u for k by u for k plus 1, right. Iteration you can update as iteration plus 1 and end. So, this gives you a set of understanding for the equations to solve for this membrane based problem. Okay, so, we had these two equations that we are solving. We had a nonlinear term. For the nonlinear term, we are iterating, taking the last guess value and iterating till the values will converge onto one set of values. Integrations, you take it using trapezoidal rule. Differentiation, you use a gradient approach. You can use Euler's approach and find out the differentiations. Okay. So, these are the plots for u versus r, and this is for different time as t is increasing. We can see that there are 11 values. I have taken the time scale of 0 to 1. This is our temperature, T or theta. This is our u. Again, our initial conditions and boundary conditions are the same. The alpha beta value are the same as that of a mass spring system. We can see that the slope over here is 0, that is a 0 slope, and it is fixed over here. Temperature is decreasing with time. All right, and therefore, we are able to solve this coupled set of equations based upon this coupled set of equations, the variations of our displacement of the membrane as a function of temperature and our temperature as a function of the displacement of membrane by iterating on top of each other within this while loop. So, this while loop will keep on going till either your error has gone beyond your error tolerance or the iteration counter has exceeded. All right, I will just touch upon thermoelasticity theory. So, for the linear thermoelasticity, we are considering a body that is directly deforming under the influence of temperature. If you have a temperature gradient within a body that is causing the body to expand, this we know very well. We know that the strain is L into 1 plus alpha delta, the total deformation is L into 1 plus alpha delta t, and the strain is L alpha delta t. So, in that case, we are giving in heat directly to a body and the body is deforming. That is the theory for the linear thermoelasticity. So, we have modified our thermal equation to include heat released from strain energy. Now, if a body is deforming, that deformation will cause heat to be released, and that heat is released in the form of strain energy. So, we can rewrite our expression for our heat transfer equation, which was k del square T, and the heat generation term we can write as alpha 3 lambda plus 2 mu T naught del epsilon k k by del T, which T naught is the reference temperature, reference or initial temperature. All right. Now, just like our heat equation is affected by the strain energy or the strain rate, in the same way our Navier's equation is affected by temperature and is written by, then you can go back to again the set of notes for solid mechanics as lambda plus mu del square ui by del xi del xj plus mu del square uj by del xi del xi minus E alpha over 1 minus 2 nu del T by del xj plus rho into Bj equals to rho into del square Uj by del T square. Okay. This equation, we had these terms from the body deformation. We have this term from deformation, this term from thermal strain, we have our body force, and finally we have our acceleration. We will pick up from here in next lecture, and we will see how we can model these thermoelastic systems using V-beam actuators, using normal thermoelastic models, and in the case of a bimetallic strip. So, thank you for listening today, and we will pick it up from this point on in the next lecture.